John. Yeah. I just okay, yeah. Thanks very much for the invitation. I'd just like to take up the discussion we had a minute ago. I think there was a misunderstanding about the time length of Varna. If you do wiggle matching, it's the same as if you do single dates. With single radiocarbon dates, you have multiple solutions. With wiggle matching, with Bayesian approaches, you have multiple solutions as well, and they have different probabilities. So you just have to find out which is the one you like best. And for me, this is a very important introduction because my approach to correspondence analysis is explorative. And if Tiziano tells us that it's probably a linear scale, I don't believe a sausage. This is exactly how I started with correspondence analysis. It was working with linear pottery experts in Frankfurt who were telling me that correspondence analysis would give you a wonderful timescale. And I said, where have you shown this? And they told me, you don't have to show it. It comes out of the theory. And I said, I'm an experimentalist. I want to see it. And that is why I started off with the correspondence analysis of Troy, because enter.
Just a minute.
Yeah.
Okay.
And I press the backwards and forwards?
Yes.
Great.
No,
the next one, please.
As the next one. This one?
This one, yeah. This is exactly why I started with the correspondence analysis in Troy, because I wanted to find it out myself. And really honestly, this mathematical stuff is quite complicated. I don't understand it, but my way of looking at it is to do experiments with it. So today we're going to experiment with the metric and the different timescales of correspondence analysis. We'll start off with Troy. I'm just working on a study with Donald Easton about the possibility of a gap in Troy. Here's the history of Troy. I'll go straight into the correspondence analysis. If you look at the upper picture, we've separated the shapes here, the correspondence shapes, from the lower picture, which is the architecture. And in the shapes we can see between Troy 1 and Troy 2, there are what we could call missing shapes. It doesn't look as if there's enough, the density is too low. If we go into the architecture at the same time in the different picture, we can see, yes, this density, the lack of density is also in the architecture. So we can guess, just as a guess, explorative testing, that there might be something missing here, which would be quite natural at Troy, with Schliemann having taken away so much of the site and Bleden having, of course, excavated selectively. He didn't excavate everything, so there could be parts of Troy we haven't excavated yet, and it could be just exactly in the transition from Troy 1 to Troy 2. And indeed, this is exactly what happened. I was very happy. I did this seriation in the 1980s, I think. I went along to Troy, invited by Manfred. I was very happy with it. And then 10, 20 years later, I started to understand what was going on here, because Manfred Kaufmann, during the new excavations, found the architecture, which I can call here missing. So it works. We're talking about the question, can we identify gaps and missing data? Let's go into the transition between Troy 3 and Troy 4 up to 5 in the shapes. Now, there's a lot of the shapes are highly dense. To me, it looks as if there's architecture missing. Yeah, it would be something like the model would be, you have a site which is functioning, every now and then a new shape is invented and used, and it goes into the stratigraphy, it's reworked and goes into our database. The architecture, so it could be that we have the pottery from one part of the site, but we have not got the architecture fitting to this pottery sequence. So for me, it's been a question for a long, long time. Is there something missing? Is there perhaps a gap in the Bleden sequence? And this is what we're going to talk about today. I'll just show you, because Donald and I have been working on the radiocarbon dates to see whether we can confirm this. here's one of these, I don't want to call it battleships, I call it spectrum, metric. These are, I call it pottery series. I don't like the military word. I'm not going to use it. Pottery series. If you now look at the pottery series, and if you look where the line is between 3 and 4, the question is for me, can in the pottery series, in their frequencies, in their development, in their numbers, can we see any gaps? And you can see here, I think, as a demonstration, which I think is quite vivid, we're going to have big difficulties finding gaps, stratigraphic gaps, architectural gaps, by looking at the pottery, because you can't see it here. So one of the big advantages about the correspondence analysis is that we have these two different pictures. We have the dots, I call them, and we have this type of distribution. Essentially, what's going on is when Benzacri developed the method in the 70s, he made this type of distribution into scores, into factors, into I call them dots. No? Our problem now is that none of the software shows us these developmental functions. And when I was working together with Reiko and Clemens in Bukova Pusta, I came up with the idea. I remembered then, but we need this sort of picture. That we need both pictures. It's sort of complementary pictures. And when I was here a few months ago, Iro said, I would like to see this as well. So that I've now sat down for quite a long time and developed the automated correspondence analysis graphic production of this sort of a picture. And it's very useful in the sense that you can play with it very quickly. Yeah, this is my experimental approach. To do experiments, you have to be able, to do it quickly. So let's go back to Troy for the moment. We have here the pinnacle, which was left over all the way up to when Manfred Kaufmann excavated it. And what I've written here, the hyena burrow site deserted at the end of Troy 3, is an indication from sites of Erdmann, the archaeozoologist, told us there is the possibility that exactly in this remaining part of Troy, there was a hyena burrow, a den. We aren't quite sure about this. It was not that clear. The interesting thing is that if it's an antique burrow, antique den, then the site must have been deserted because you don't have hyenas walking around in the main square. Hyenas are very scary animals, they'd run away. So if it is a hyena burrow, then we've had a site desertion, which would speak for a gap. We don't know, we can't prove this. You can see what happens since 1902. The first thing that happened is in the Hellenistic period, they cut away large parts of Troy 4 and practically all of Troy 5. That's still remaining 1902. And then since 1902, we've lost further parts of Troy. So to solve or to resolve, to look at our study, our Troy 3-4 gap question, we can't use the pinnacle. What we can use is what is Blegen calls the island. We can see it here. I've put the periods 2, 3, 4, 5. There's quite a bit. Practically all we have in the Blegen publications of Troy 4 and 5 come from this excavation. What you can see in the foreground here, that's the Temenos. We're in Troy 2 here. Okay. Here's the excavations. The top is the excavations in 1933, Troy 4. You look down, and then after the walls of Troy had been removed, we can see in 1935. At the top right, you can see the sampling we've done in the excavations, which are not there anymore, of course, so we had to go into the museum. I'll tell you in a minute. And here's the stratigraphy at the bottom right. No? Here's a very informative picture, which was made by Peter Pavuk. I should mention that I had I'm very happy to be able to work with Peter Pavuk's father. And that was my first correspondence analysis because he was working in the Neolithic Sturovo course. So here's the son, Peter Pavuk. What you can see in the middle here is the pinnacle, and Peter has made two pictures of it. On the right one is the older one, 1902, and then it's a bit later, what's left over. At the bottom left, you can have the different periods in 2 and 3 and 4 and 5. And since Ilios and Sturpfel has been changing all the time. But what we are now doing, Donald and I, we are using Peter Pavok's terminology. So if we talk about Troy 3, in Ilios, Sturpfel might be talking about Troy 4. You have to be very careful. You have to be aware of this. No, it's the picture in the middle here is where the pinnacle has been excavated all the way down. Here's the Schliemann bench. This is the Minoan 2A, and then on the right we have the pinnacle, the island. What we have done now, and what Donald did with the help of the Osteo-Archaeological Research Laboratory in Stockholm with Jan Stora, we were able to get bones from the original Blegen excavations, which the archaeozoologist Gijwal had taken. He was there on site, I think 33, 34, 35. But anyway, the bones were taken to Stockholm in 1937. They are documented there, and there are copies of the documents, must be hundreds of kilograms of Troy Blegen excavation bones in the department, and the documentation is in Cincinnati. I must show you this here. If you look here, middle 3B. Yeah? This is Blegen's original writing. So we can go, or rather the people in the museum can go in, give us bones which belong to what we could call Blegen's language, certified 3, 4. And we've done that. And altogether, we've got something like 28 new radiocarbon dates. I've done modeling here, the normal wiggle matching modeling. I've written it down here. Monte Carlo, 750,000 models. It runs overnight, 8 or 10 or 12 hours. These pictures are always a bit sort of not quite easy to read, because you must not, please imagine that if we do not know if we only know the phase or the period, we have to take all the samples we've got from the period and give them a random position inside them. So it's running random positioning all the time. And I can only then show the picture. I just show one of the statistical sampling procedures which happens. So there's many. And altogether, the bottom picture, the red one, I'm quite happy with. It's something which I'm using all the time now. Developed it last year together with Stefanos in Sidon, and is that we take the IntCal data. You can see at the top it says there's set 1, Queen's Laboratory, set 2, University of Belfast, Pretoria. What I'm doing here, I'm taking, because I don't believe in the smooth calibration curve, which the IntCal group are often giving me, but I don't want to produce new ones all the time myself, and I haven't got the data anyway. So what I do, I take the internationally recommended calibration curve, but then to analyze the radiocarbon dates graphically, I plonk the raw data on them with a certain menu, and it goes very quickly, a few minutes. And then what I've done here now, in new algorithms, is that I take the window, in this case from 2500 to, was it 1500 BC. If you have a big data set and you're looking at this selection of the data set, every data set which is a part of the calibration curve has its offsets. It is either a bit too low, a bit too high, and this and that. And I'm using an automatic filter. So whenever I choose a filter on the screen, a screen view, it automatically uses the screen as the filtering. So I can tell you, for example, the Queen's Laboratory data. In this window, there's 138 measurements, and on statistical average, they're 2,3 BP, either above or below. 0.1 BP is 1 month, so that we have radiocarbon months as well, if you want. And so set 2 has -15. Set 6 has 8,3. It's just the statistical deviations. We are looking very carefully nowadays at the offsets of the laboratories. which participate in the calibration curve construction. It could be there are problems of the that we have to unify the calibration curve, not only in terms of the laboratories which are participating, but we have possible international or global differences in the contemporary radiocarbon atmosphere. If you go to the equator, the air goes up, the carbon dioxide goes up, and it comes down again. And there's lots of minor differences on the scale, probably with a few radiocarbon years, perhaps 10 years, 20 years ago, or 10 years ago, it was expected that we have differences up to 20 years between Egypt and the Levant. We don't. We have it at the most 10. But this is the sort of stuff I've automated now. So every time I do a wiggle matching study, I do this sort of study as well. And you can see that the laboratories at the top have a few radiocarbon years offset, -15 is the maximum. And our data set has a weighted offset of 17 and a pooled offset of 13, which is normal. It's perhaps a bit too high, but it depends on the model. No, of course, if we move the samples backwards and forwards, then their pooled weighted offset will change. No? I don't want to talk too much about the radiocarbon, but here is a zoom into the model. And for the moment, I've convinced myself, at least, I don't know whether you're convinced, but I've convinced myself that there is a high likelihood that there really is a gap in the Blegen pottery sequence. No? The remaining difficulty, we can't be sure yet, is simply that we still haven't got any radiocarbon dates from the gap, and you can't date gaps with radiocarbon because you don't get any samples. So, the seriation and the statistical techniques give us a certain chance of that we are not dependent on hoping that the previous chronologies are all correct. Now to the second part of what I want to talk to you about. We have here Jean-Paul Benzacri. He's the inventor of the correspondence analysis method. It was his PhD, 1973, it's 619 pages. I haven't read them. I've been playing with the computer programs. From my perspective, statistics is a tool. It's like a hammer. You don't have to understand every hammer you're using. It's better to understand it. Okay. What I think is more interesting, we can look at maths as a language. If you ask people, is mathematics is it natural sciences or cultural science, they will tell you, no, it's a language. So if you have a language, you need translation. And that's why I'm talking about translating now. The picture at the top on the right, we have the dots. At the bottom, we have the distributions. And what I'm working on at the moment is to produce these distributions as quick as possible, but what makes it a bit difficult is that there are different possibilities, and I've put the possibilities here, and I want to show this in a graphic animation. We can choose the input table for testing purposes as counts or as incidences. Graph 3 is just a projection down of all the scores. The projection, the graph 4 is the numbers. If you develop software, if you want to look at your data, it's quite good to have it on the screen. Then you can see not only the distributions, as in the lower right, but see exactly how many pieces of shirts do we have or pieces of metal. Then comes the ominous polynomial projection, which is my favorite, and I'll show you why. And then we have the rotation. I'll just go one step forward, then you'll see what's happening. Here's the menu. That's the polynomial. It should be running now. That's the projection of the scores onto the polynomial. Now we can make a scale running along the polynomial. We can let our pottery run along the polynomial. Then we can turn the polynomial. And what's really interesting about this is that if you look into the lower graph, if you turn the polynomial, the projection changes. But if you, perhaps I can go back, let's start it again. A moment. So now, take the top picture, look at the barcode at the top, polynomial projection. If you turn the polynomial, the projection of your scores onto the polynomial does not change. For me, this is an experimental demonstration, a bit of a hope that my software programming is working. It does not change. So this is, from my perspective, the natural experimental choice, because if you do a projection and you can change the rotation of your CA, you're going to get a different chronology every time. How do you calibrate this? Oh dear. But if you have if we can show that the polynomial projection works nicely, then there's only one solution. Wonderful. So this is what we're going at. We want to demonstrate the theoreticians tell us that the polynomial projection is going to be the best. My problem with this sort of theoretical explanation is we don't only have two factors, we have 3, 4, 5, and I don't know how many. So which polynomial projection? We are doing a very simple polynomial projection onto 2 factors. So we'll try it. This is now the different methods. We'll start off with the input table, just the numbers. Then come the counts, more or less. Then come the factor 1 projection, just straight down. Then comes the same with numbers. Now comes the ominous polynomial projection. So, that would be a finished solution. And then we can rotate the system. I'll just show you one rotation here. Then we can change if you have a table, you often need it this way, that way, the other way. You want to have the oldest at the bottom left and the youngest at the top right. I want to do this with one button, so clack, clack, clack. And then you can, when we're finished, we can then choose which is our favorite, hoping that the polynomial projection will be the one we choose. So I'll now show you some experimental correspondence analyses to check on this question. Here's the Troy 6-7. You can see is it a jar or jug or something? The B25 counts are over the different phases. If you look at the table and compare it with this diagram, this Pottery series, not battleship, then you can see it's correct, because we have a lot of counts in the early Troy 6, and we have them in the Pottery series diagram as well. So that confirms that the polynomial projection corresponds to our data. I'm not making any programming mistakes, I hope. Let's now compare. On the top right, we have the polynomial projection. And on the bottom right here, the factor 1 projection, you can see here, we have counts here, but they're missing in the projection. That is because of a complex way of twiddle and turn. There are certain things happening which you don't necessarily see immediately. So we have here a direct confirmation that the polynomial projection is, I wouldn't say that the better chronological result, it's the one which corresponds to the data. And that's important for me. I want to see the data, and then the calibration or the chronology comes as a last, as a next step. So at least the data is better represented by the polynomial projection. This is exactly what Raiko and Clemens told me. I learned from them, that's why I'm doing it. And it works. This confirms the theoretical explanations. No? We have now, if you calibrate this onto calendric years, we can see we're getting something like plus minus 30 calendric years. So already now this dating is much, much more precise than radiocarbon, except it hasn't got the calibration yet. It hasn't got the age calibration, which we still need. Let's now have a look at Foromark 1972. He has motives and he has shapes. This is my way of counting in the Mycenaean pottery. On the left, you can see the world shell motive. You have to abbreviate the names, then you have a count, and I went through the whole of the catalog and counted the whole stuff. On the right is the counting for the shapes, where after a while you get used. We were talking about this yesterday evening. The difficulty with Foromark is that there are very few shapes for LM1A. There aren't many at all. Oh dear. So, please don't bother too much about the terminology, because I've learned myself the hard way that he has a different terminology than people have 20 or 30 years later. So anyway, this is how I did the counting. And these are now the correspondence analyses, the results. At the top 314 shapes, you can see the development 1, 2A, 2B, 3A, 1, and so it works. Okay, just about, yeah. Then we have the motives, separately, 1744, which is completely redundant, because I haven't got it's a very, very loose low density table. And then I've made an even bigger table where I've just taken the shapes and added on the motifs so they're both together. I think it's a bit better. It looks nicely. For example, if you look at the shapes here, 3, 6, CA1, they're closer together, they're further apart again. Sometimes one LM1A and 2A switch, so they're very wobbly. I'm a bit skeptical about dating with this sort of method. If we go into the Santorini problem, we probably couldn't use it. No way at all. We have to be realistic. We can't use it. Let's now go a step further. Penelope Mountjoy, 1999. This is something like 18 volumes, and I'm very pleased that Reinhard sent me the PDFs. So I was able to work through them. So I've counted I'll show you more pictures in a moment, but what I've done here, Penelope has got a second paper where she's had a very close look at Troy, and she has what I call forum-archized Troy, the Trojan material. She's looked at Mycenaean pottery in Troy, and she's come up with a solution that Troy 6H is equivalent in age to the later Late 3A2. I've run it in the seriation. Yes, it works. It comes out quite nicely. And I was also quite interested in the result that Penelope writes that other possibilities of dating Troy 6H often go, or earlier researchers go more towards the LH3B1. There are elements there as well. So of course you have, these are not just sort of blockwise dating. You have a lot of material which is LH3A2 as a center of gravity, and then it's statistics. So even the statistics works out nicely. At the bottom we have the projection. I would call it plus minus 20 years. It sounds quite good, but it's not, because a 2 sigma interval is 80 years. If you take a bucket of sherds and you can date it within 80 years, it's not what we want. It's not enough yet. We can't solve many problems. And talking about what to do with correspondence analysis, this is not my topic today, but I still see the classical, traditional method of manual perspective, dating, visual dating, impressionistic dating, we could call it, still today is much, much more precise, because the people who do this know their pottery and I don't. Yeah, what I can show you that is, I think I'm hoping a bit that we can combine the two approaches. No? Now to the question of the linearity. At the top, we have the factor 1 projection. Then we, as an option, you can see here, big changes in pottery. We were talking about this question yesterday. I would like to make you aware of the fact that in Penelope, pottery classification has exactly the same properties as Forumark. Of course, it's based on the same stuff, which is interesting for me because there is one very big transition. The biggest change in both of these volumes in the pottery is from later Ladic 3A1 to 3A2. That is where you have, it really is the matrices, the tables separate. It's as if you have two periods. This is the earlier, this is the second one. And I've been reading a bit myself. This is in the palatial system. Somehow the pottery changes in a way that I can see in the numeric data. At the bottom left, I can put in equidistant phases. That's the bit complicated. I was testing. Is this scale, are any of these scales linear with time? I've come to the conclusion to a certain extent, it's an ordinal scale. Yes, it sort of comes later. Perhaps every now and then a switch. If we try to make it into a metric scale for wiggle matching purposes, it doesn't work. It really doesn't work. What have I written here? CA produces a reasonably correct ordinal timescale, younger, but CA factor space is presently not useful for purposes of metric timescaling. And that is a very crucial point, because that tells me that I'm not going to use my Gaussian wiggle matching programs on radiocarbon dates of this type. I would go over and use Bayesian sequencing. Okay, yeah. And finally, I'd like to point out, show you that the probability, the whole of all these bodies are non-linear. If you look at the top right here, that one, this one, it's exactly the same data in a different representation. I'm going to zoom into this just to show you. Pottery series graphs make use of non-linear probabilities. Identical phase percentages are shown with different areas in the projection. Yeah, you can see here, for example, at the bottom right, the two areas here, yeah, have a certain relationship to each other. The relationship is different here. So it's not linear. If we look at these pictures, our eye is being distorted. Mathematically, it's exactly the same question. I'm not going to go into more detail of this. Is of the most recent KDE, what's it, by Oxcal Bayesian approach, which gives us spikes. You know, these radiocarbon distribution, you have large spikes on them. And this is because the mathematics of the area normalization in the background is wrong. It really is wrong. I can say this because it's a Fourier transform we're looking at in radiocarbon dating. I have the impression also that the transition from dots to distributions in correspondence analysis might also be a Fourier transform, which makes it very interesting for theoreticians like me, because then you immediately go into quantum theory. Yeah, that's why I've put in the top left. Why do you need the B? A is equal to B. Sabine Hossendorfer. Do we really need B for bias? Thank you. Thanks for your time.
Hello? Yes, okay, that's fine. Thanks very much for a fascinating paper. I'm sure there'll be a lot of questions. I like, by the way, your nod to, let's say, more traditional approaches to ceramics as impressionist dating. This was very nice. So who would like to start off the questions here? And are there any questions online?
Thank you very much, Brennan. This is very interesting and the potential that you present. So you want, in fact, to make a program for having these battleship diagrams.
Yeah.
This is your goal.
Yes. I've finished. I've finished.
Are you finished?
Yes. You take a table, you look at the CA scores, you press another button, choose one of these options, and you get your picture. The remaining problem is that the large majority of data sets I've got for this type of study doesn't make very nice pictures because they're much too low density. If you haven't got enough data, you don't see a nice pottery series. Yeah, that's all.
It doesn't matter. It's the method that counts, and with more data.
Yeah.
Something else. The data project, the projection. You'll do the projection in CalPal.
Oh, I've got it integrated in CalPal because I've got for me, it's just it's a convenient way of programming. Why should I separate it into 5 different programs if I want to combine them anyway? Because, for example, what I can now do easily is just take one of these diagrams and put a climate curve underneath it. Why not? Yeah, just to look whether the gap is climatic 4.2 or whatever. Yeah, it's quickly done, and you don't have to change your program. That's all.
Okay, yes. And the factors, when you add the factors, are they artificially? Are they how do you add the factors? On which grounds? It might be a long question. It might be
what I do is the same as everybody does in past, for example, the CA program. I'm using Andreas Zimmermann's Fortran software. And you run a CA, and then you get this score diagram. The factors, I mean, this is the standard question I have as well. And Reiko had a good go at answering it. There's perhaps another way of answering it. If you look at a table which is seriated, they are all close to the diagonal, yeah, which tells you there's some sort of very high correlation, yeah. There's a correlation between the rows and the columns. And the closer the diagonal is, the higher the correlation is, of course. And the moment you get correlations of this type, you can do it in different higher order spaces. It's just a matter of choosing a factor means you are choosing a certain type of correlation, a direction of correlation. Perhaps that helps you. It helps me, at least. I don't really want to know what the factor is because please don't forget, this was Benzekri's PhD. I don't know if anybody understands my or your PhD. I don't understand it. I don't understand it. I don't.
The point is that you need to know your material.
Yes, exactly.
Very well.
That's what I call the explorative, the experimental approach. The archaeological data is in the front. We look at the archaeological data from the perspective of a microscope. We call a statistical seriation. It's like
Thank you for a very interesting talk. I was really interested to see where you showed the InkCal per raw data.
Yeah.
And you talked about the offsets that are
Of course.
combined and built into InkCal. And we're learning more and more about these, particularly as we go, as we make this change from those decadal blocks of data that you're looking at currently in your time period of between and then moving into single year radiocarbon data.
Yeah.
And we see the offset in the single year data as well, hopefully on a slightly lesser scale. And they all, hopefully everything will tighten up, get more and more precise as the InkCal calibration curve is improved with single year data over the next few years. But I really liked what you did there, and I think that's very, very smart to find the offset in your data set. And I wondered if you thought about using the sort of that oxcal delta R on where you can actually see there's a clear offset when you plot against the raw data. If you calculated the difference between your raw data offset and the raw data in InkCal, and then you use that for the delta R in oxcal, perhaps that would give you a slightly more refined result.
I'm not quite sure whether I'm understanding you correctly, but what I can say is there are certain papers by Sturt Manning and by D, which I've been reading very intensively because it was quite tricky programming. I know that I'm not using oxcal myself, and it's a wonderful program. And I know that what was the function, R function or something? Delta R, yeah. I used the published delta R results to calibrate, to make quite sure that my calculations are correct. And as I understand it, you have to go into oxcal and give them another data set and another data set and another data set. You do it by hand. And what I'm doing is automatic. I've automated the whole thing, and I've checked my results of delta. What is the delta R? The differences between the two data sets. I've checked down to the second decimal position. So I'm very sure that I can take any, just as an example, of the InkCal data sets, call it data set number 15 from Japanese trees on this and that, plunk it onto the calibration curve InkCal 22, or change the calibration curve. Just you can change the calibration curve and get another delta, what you want. And then I'm not always interested in the whole of the data set, because some data sets are 5,000 years long, and then you have two more there. I'm interested in this very specific interval for the archaeological data, for example, in the Near East. The early Iron Age between, say, 1100 BC and 900 BC, I want to know the offsets in this region. So I'm using that's what I mentioned, the screen as a filter. So you do your wiggle matching, plonk it into the computer, then you choose the data sets of InkCal that you need. And then it tells you automatically what the delta, what you call the things, I forget. Yeah, for me, they're weighted averages. Yes, and that I can really say it's very convenient to do this. It's probably, I'm hoping that we can find out more at the moment to answer the question you have in mind, at least I have in mind, and many people have in mind, whether we can actually measure the environmental effects, the atmospheric effects. At the moment, I don't see anything at all, and this confirms pretty much what Sturt Manning, what I've been reading. The last papers are 2 years old. Perhaps it's plus minus 10, and we don't know. We cannot demonstrate anything at all in terms of atmospheric effects on radiocarbon data sets. What I can see sometimes, it's, I mean, we're in a global universe, that the Japanese measurements, and I'm pretty in the laboratory offset, could be different to the Irish ones. Why not? But I don't see any results yet that I can build on. If we could build on these results, and I'm bringing owls to Athens for you, if we can demonstrate the effects, the existence of interlaboratory offsets on a level of 10, 15 years, if we can show this, then we can use them to correct our chronologies. Of course, at the moment we can't. I don't think we can. All we have to do is to make a documentation of their existence.
Great. Thank
Do
very
you
much.
agree with that?